And today's speaker is Georgii Riabov with the talk on modifications of Burdzy-Kaspi stochastic flows. Please, Georgi.
Okay, so in this talk, I will discuss my last result on existence of strong flow modifications of stochastic flows and its applications to Burdzy-Kaspi stochastic flows. So I will start with the definition of a stochastic flow. Let M and ρ be a locally compact separable metric space. By F, I will denote the space of measurable mappings of M equipped with a cylindrical sigma field. So a stochastic flow on M is a family of regular random elements in F. So it is a family of random mappings such that following five properties holds. First is a weak evolutionary property. It means that the composition of two mappings from the flow is almost surely equal to the psi RT. Okay, where the exceptional set may depend on time and on the space variable as well. Also, mappings act independently on disjoint intervals. The distribution of the mapping depends only on the difference t minus s, and two more properties are equivalent to the Feller properties of finite point motions of the flow. In the sense, it will be defined now. Okay, so a stochastic flow can be defined through its finite point motions if we consider endpoints from the space and a set in M to the power n, then we can define this probability, and it turns out that this probability, it is a Feller transition function on M to the power n. Moreover, these transition functions they satisfy a consistency property in the sense that if we know the distribution of n functions, n point motions, then we know the distribution of k point motions from the flow. And one more property is that if we start from the same point, then we the trajectories of the flow are equal. Okay, and there is a one-to-one correspondence between sequences of Feller transition functions that satisfy properties 1 and 2 and stochastic flows in the following sense. I will be interested in strong stochastic flows for which the evolutionary property holds without exceptions. It means that with probability 1 for all times RST, the composition of mappings psi RS and psi ST is equal to psi RT. In what follows, I will consider stochastic flows with continuous trajectories. So I will assume the condition 3. Okay, and by CIM, I will denote the space of continuous functions from some interval I to M. By X, I will denote the space of all paths in M. This is a Polish space with respect to the metric of uniform convergence on bounded intervals.
Jürgen, what is M? Locally compact space?
M is a locally compact separable metric space.
Thank you.
But today I will consider mainly the case when M is just R. Okay, and last time I showed that there exists a measurable mapping L that sends every relatively compact sequence of functions into its limit point. So I will use this mapping in the future, and if we consider a sequence of path, then by Sn I will denote the initial time of a path, and by Xn I will denote the starting point of a path. Okay, and I of S will be all paths that started before time S. So now a sequence of functions will be called a skeleton if the following three conditions hold. So first of all, if two trajectories from the skeleton meet at some point S, then they must coalesce after that. Second condition is that the set of starting times and starting points is dense in the product of time and space. And one more property is that if we consider the set of all functions from the skeleton that been in some compact set L, then this set of functions must be relatively compact in the space of the trajectories in X. Okay, so now S denotes the space of all skeletons, and last time I proved the following result, that there is a measurable mapping theta that for every time S and for every point X, it produces a path in such a way that theta Sx is actually a continuous path in M that starts at time S from the point X. Moreover, if the starting position is in the skeleton, then this mapping preserves this path. And here I remind how it can be constructed. So by NSXK, I denote the first trajectory that was in epsilon neighborhood of X at time S. And phi is the continuation of this the trajectory after time S. Then we can just take these the trajectories and choose a limit point in a measurable way. Okay.
Georgi, excuse me,
Yes.
what is the distance or topology in the set of skeletons? Because you say that you have some space of all skeletons and that you use measurable mapping and so on.
Yes, so the distance between two paths
Yes, I understand, but between skeletons. You said,
Yes.
can you show the previous slide? Oh, SM denotes the space of all skeletons.
Yes.
So what is the distance or topology in space in the set of skeletons?
The space of skeletons can be considered as a subset of space of sequences of paths.
Mhm. Okay, with
Uh,
induced matrix.
Yes. Yes.
Okay, thank you.
Okay. So now, if we take some stochastic flow with distributions of finite point motions given by some sequence of failure transition functions Pn. Also, we take a dense sequence of starting times and points, and we can consider all the trajectories from a stochastic flow that started at times Sn, points Xn. Okay, so this is a family of continuous functions, so we can consider it as a random element in the space of sequences of continuous functions. And I will assume that with probability 1, this sequence is a skeleton. Okay. Then one can define, for example, such scale epsilon k of x at every point. And after this, applying the mapping theta to this skeleton phi, we get a modification of a flow psi 0. And the result is that almost surely theta is equal to psi 0. And moreover, as a function of all variables s, t, x, and omega, theta is a measurable function. And one more property is that the mapping theta preserves the trajectories from the skeleton. Okay. Now I will define one more object. So by k st epsilon x, I denote the closure of all the trajectories from the skeleton that were in the neighborhood of x at time s. And by k stx, I will denote the intersection of these sets. By our assumptions, it is a non-empty compact subset of continuous functions, and it always contains a theta. Now, by nu, I will denote the number of elements in K, and by tau, I will denote the first time after S, such that the number of elements is greater or equal to 2. So it's like the bifurcation times. So by E, I will denote the set of bifurcation points. It means that these are points Sx such that immediately after time S, we have a possibility of bifurcation. And I will assume that there is a closed set F such that with probability 1, F contains all bifurcation points E. Okay, so by sigma, I will denote the heating time of the set F.
Georgii, excuse me, what is F? So we select or?
No, I just assume that there is a closed set.
Why it cannot be R multiplied by M?
It can be.
It can be.
It
So,
can be. Yes.
so just consider such closed subset Z.
Yes. Yes.
Mhm.
Yes.
And is it a random event that you say with probability 1 E is a subset of F, or
It means that there is an event of probability 0, outside which, for all omega, E is a subset of F.
okay?
And F is a non-random set.
Mhm.
Okay.
I'm sorry, I have another
Yes.
question. Nu S T of X, can such numbers be infinite?
Yes.
It's possible. Okay, thank you.
We are interested only in the case when it becomes greater than 1.
So it's maybe immediately S.
Yes. Yes.
Okay.
Okay. So and sigma is the heating time of the set F. And last time I proved the following result. So the mapping psi is defined in the following way. Before time sigma, this is theta, and exactly at time sigma, we impose the strong evolutionary property. Then, if almost surely for all S and X, the following holds. So if after time sigma, the flow hits set F, then immediately after that time, it coalesces with the trajectory of the skeleton. So under this condition, psi satisfies the strong flow property. Okay. So as a consequence of this, we show that there are strong flows of coalescing independent Walsh-Brownian motions on a metric graph. However, there was one case where we didn't have this condition to hold. So now I want to discuss this condition. Now let B be a two-sided Brownian motion. We fix some dense sequence in R times R, and beta will be a number from -1 to 1, but not 0, because the case when it is 0 is obvious. And by F, I will denote the product. So time is any, yes, and the space is 0. Okay, then it is known by Harrison and Shep that the following system has a unique strongest solution. So here, phi n, it's a skew Brownian motion. It satisfies the equation that d phi n equals to dbt plus beta times d ln of t. And ln is a symmetric local time of phi n at 0. I want to show that this example does not satisfy our assumptions. Okay, And I can show it in the case when beta is equal to 1. In this case, we get exactly a reflected Brownian motion. So this equation can be solved. And actually, phi n is equal to x plus bt minus bs before hitting 0. And then it is a reflected Brownian motion. So it is b minus the minimum of b. Okay. Now, I will change a little bit the definition of strong flow of a sequence of approximations that we use. So by n, I will denote the first the trajectory that was below x. Okay. And again, by then we construct this sequence of trajectories and choose a limit point. In this way, we also get a flow, and this flow preserves trajectories of the skeleton. However, let us consider the following case. So by tau, I will denote the point where the Brownian motion achieves its maximum on the segment 0, 1. Let us note that minus b of tau is never equal to the trajectory from the skeleton. So we will approximate the trajectory from this flow from below, and as a result, we will get that theta of minus b of tau is equal to b of t minus b of tau. In particular, it hits 0 exactly at time tau. So after we define the flow psi, it will be always below 0 after time tau. So
Georgii, excuse me,
yes.
is beta 1 now?
Yes.
Yes.
Thank you. So this reflecting flow is does not satisfy your property,
No.
or does?
No. No. This is what I want to show. So if we have beta equals to 1, and if we approximate trajectories from below, then the property from the theorem will not be true.
Could you please recall us this property? Which property fails?
This one. So this means that after we hit 0 after time sigma, then we must coalesce with the trajectory of the skeleton.
And you state that we don't.
Yes. Yes. In fact,
and could you please make a picture one more time? I can't understand why this happens.
Because if this is the point of maximum of a Brownian motion, and if we start from the point minus b of tau, then we will hit 0 at time tau, but we will go under 0 after that.
Okay, I see. So we consider reflecting. So if you start from above, you will be above 0 always. But if
Yes,
you
yes.
start from below
Yes.
and hit 0, then theoretically you may cross 0 or you may not if you touch.
Yes, but if tau is a time of maximum, then we will go below 0.
So below 0, there are different reasons to go out of the line. Yes.
Yes.
Mm-hmm.
So we will not get a strong flow using this definition of psi.
Mm-hmm.
Okay. So and actually this example shows the way to improve it. I will consider two strong flow modifications, two modifications of a stochastic flow. So NSX plus is the approximation from above, and NSX minus is approximation from below. Using these two approximations, we can define two flows, theta plus and theta minus. And it was shown by Burdzy and Kaspi that almost surely for all S and X, theta plus and minus, they satisfy the Harrison's-Shep equation. Moreover, L plus is the supremum of the increments of local times of trajectories that approximate X from above, and L minus is the supremum of local times of trajectories that approximate X from below.
And this exceptional set, does it depend on S and X?
No, no. So they proved that with probability 1, this holds for all S and X, and for theta plus and theta minus. Moreover, they proved that the following properties hold with the probability 1. So for all S and X and all times T1 bigger than S, there are two possibilities. Either the local time L plus is equal to 0, or after time T1, theta plus is coalescing with one of trajectories of the skeleton. And the same holds for L minus and theta minus. Now, let us note that if at time S, no trajectory of the skeleton is at 0, then either L plus is bigger than 0 for all T bigger than S, or L minus is bigger than 0 for all T bigger than S. And the proof of this is actually simple. So if L plus and minus ST of 0 is equal to 0, then from the construction of theta plus and theta minus, we must have that the increment that theta plus is BU minus BS, and it must be greater or equal to 0. And at the same time, theta minus must be BU minus BS, and it must be less or equal to 0. But of course, this is impossible. And as a consequence of this, we can define the strong flow modification of the Burdzy-Kaspi flow using two different approximations. Okay, so before hitting 0, we can use either theta plus or theta minus, and after hitting 0, we can look at L plus. So if it is bigger than 0, immediately after sigma, then we can apply theta plus. If it is equal to 0 for some u greater than sigma, then we can apply theta minus. The point is that in the third case, L minus might be big. L minus has to be bigger than 0. So in each case, immediately after time sigma, we coalesce with the trajectory of the skeleton, and it means that this modification psi satisfies assumptions of the theorem 3. So this is a strong flow, and this is a strong flow modification of the Burdzy-Kaspi flow.
Georgi, I have one more question. So as far as I remember, Burdzy and Kaspi prove that there are some lenses in this flow.
Yes,
Is it true?
it is true, but
So could you please
this-
explain what is lens and what is relation of lens and of this strong flow?
okay, so a lens is we say that S is the initial time of a lens if we have the following property. Okay, for some S less than T less than U. And theta plus SU of 0 is equal to theta minus SU of 0. So when we have this point S, we call that this is an initial time of a lens. This is theta plus, and this is theta minus. Okay.
And what about your skeletons and strong flow of modification?
This definition tells, in some sense, at this point, in which way to go. Okay.
So so you select upper if the local time is positive, or lower if the local time is 0.
Yes. Because in the last case, the local time of negative is bigger than 0, so it must coalesce with some trajectory from the skeleton.
Thanks.
Okay, so this I think that this can be extended to the case of Tanaka flows on metric graphs. When we have a metric graph and we have a branching and some at some points, okay, and what must be checked is that immediately after hitting the vertex of the graph, we must coalesce with the some trajectory of this skeleton. So in the case of Tanaka flows of metric graphs, we don't have theta plus and theta minus, but we have like theta 1, theta 2, and so on. So I assume that this construction can give strong flows, strong modifications of Tanaka flows on metric graphs. Okay, so this is all that I prepared for now. Thank you for the attention.
Okay, thank you very much. Maybe somebody have questions or comments, please. If no, I want to ask about the set of breakpoints. In case in your example and in metric graphs which you propose to consider for Tanaka equation, this set where something bad can happen consists of isolated points.
Yes.
Can you see? Can you discuss? Can you consider more complicated cases when this set will be non-countable, for example, something?
When we have instantaneous coalescence, then actually we don't care about this set. So we just take R times M.
Okay, yes, but in those cases you have some strong condition which does not allow appearance of
Yes.
this.
Yes.
But it will be interesting to have such a picture when such double points can appear in much more rich set.
Yes, yes.
Because here you make the correction just using different reflections from above and from below, and you use like indicator of this. You use the local time for trajectories from the skeleton. But we can define the local time on a much more rich set, like a counter set or something, yeah. And
Yes.
maybe it can help.
Okay.
Okay.
Thank you. Thank you.
Thank you very much again for the talk, and we will wait for a new strong flows. And the next speaker, as far as I remember, will be Anastasia Grabovets.
No, next speaker
No?
is now Felix.
Oh, yes, yes. Okay. So she will be at March 28, I think, and Noafel at March 21 with some properties, large deviation for generalized local self-intersection local types of Brownian motion. Okay, for today this all, and thanks everybody, and see you next week. Bye.
Goodbye.
Bye-bye.
Goodbye.